This is a presentation for the course Topics in Data Science. My name is Zubin and I am a PhD student in the Computer Science department at UMass. I'm going to talk about Deep Neural Decision Forests. This paper was published in the International Conference on Computer Vision in 2015. I'll start with the basic introduction followed by the proposed approach discussed in the paper. Then I'm going to talk about the experiments and results followed by the conclusion. So this paper proposes a model which combines two very different paradigms of machine learning, deep neural nets and decision trees. Neural nets and decision trees are both very powerful classes of machine learning algorithms, but they are very different in nature. Deep learning approaches, CNNs to be more specific, learn hierarchical representation or features of the data. However, decision trees are characterized by a hierarchical clustering of the data. It learns how to split the data's input space in a hierarchical fashion. So neural nets learn complex nonlinear transformations to apply to input data in order to enable easy and accurate classification or regression. So here in this example of a neural net, we see that CNN learns a range of features at different levels. So initial layers learn very basic features, while the layers which are at a deeper level learn more complex, nuanced features. And on the right, we have a very simple example of a deterministic decision tree. Each node here represents a condition. These are called the decision nodes. So based on this, the sequence, the path of the decision would be followed, and in the leaf we get the predictions. So when we use a bunch of these decision trees as an ensemble, we call it a decision forest or a random forest. So the idea here is to use representational learning functionality of convolutional neural networks and combine it with the decision forests to get the final output. Training here is done in an end-to-end manner by optimizing for a global cost function. A point to note here is that instead of a traditional deterministic decision tree, stochastic differentiable decision trees are used, which are compatible with the backpropagation algorithm. So in this next section, we'll see this idea in much more detail. So the model proposed in this paper has two distinct parts, a CNN part and a decision forest part. The CNN part can have any kind of convolutional layer, pooling layer, and even fully connected layer if there's a need for it. But instead of a fully connected output layer, it has a decision forest layer. For a given sample or input, each of these trees in the final decision forest layer gives a probability distribution over class as output, and each output of these individual trees is averaged to obtain the final output. As previously mentioned, the decision trees used here is not the traditional deterministic decision tree. Instead, a stochastic version of the decision tree is used. So in this stochastic version of the decision tree, each internal node has a probability associated with it. And all the leaves have a learnable probability distribution over a set of classes. Here is a simple example which shows each node to be associated with a decision function. So this function dn is like associated with a node n. So this marked path shows the routing for an input x from d1 to d2 to d5, ultimately to the leaf node L4. So this probability of this routing is given by the product of the probabilities associated with each node. So this figure shows how the internal nodes get their respective probabilities. So for each tree, a predefined fraction of the neurons from the previous layer is selected. These are further connected to a fully connected layer as shown here. So yeah, so the number of neurons in this layer is exactly equal to the number of internal nodes in the trees. So another point to note here is that the number of trees is a hyperparameter which needs to be fixed before execution. The output of this layer, this fully connected layer, is passed through a sigmoid function, and these values are used as probabilities of the internal node. So this Fn represents the output of these neurons of the fully connected layer given the parameters theta passed through a sigmoid function, and this determines the probability or the value of the function dn for node n. So this is like saying that this is the value of the probability of a given node. Yeah, so each leaf node is associated with a probability vector pi I for each classes. A forest, like name implies, consists of a large number of trees, decision trees in our case. So these group of decision trees operate as an ensemble. The idea here is that a large number of uncorrelated decision trees operating as a committee will outperform any individual trees. The output of each tree is averaged to arrive at the final result. So this expression shows how the final result is computed. So this would be the result of each individual tree, the probability distribution predicted by each individual tree, uh, which is averaged, and this gives us the final result, which is this P of F. Yeah. Backpropagation. So learning in decision trees involve learning both the decision node parameterizations, the theta, and the leaf predictions, the pi. So given a dataset T, we try to minimize the R, the risk, under log loss, so which is this L. So basically we search for the minimizers of this term. So we like to minimize this. So the authors also implemented a two-step optimization strategy which alternates between updating theta and pi. This is because the parameters needed to be learned is theta and pi. If pi is known and fixed, we can train the model like it was a normal neural network model, simply using backpropagation. But that's not the case. So the authors propose a training strategy which is to first update pi and while doing this, theta should be kept fixed, and then theta should be optimized using the objective function uh, while keeping pi fixed. Okay. Now let's look at the learning procedure, the algorithm which is used to learn the theta, the parameters of the trees. So this is like traditional backpropagation algorithm. So given the training set, the data set, and the number of epochs, we start with uh, random initialization of the theta values, and for each epoch we compute the pi by iteration. So this is basically a convex optimization problem, and we are trying to find the global minima. So the iterative scheme which was described is used to compute the global minima here. So mini batches are used. I mean, the data is broken into small batches which are used to train. Uh, so in this step, in step 6, we see uh, stochastic gradient descent being used to update the theta values. So next we'll discuss the experiments and results of this approach. So one experiment which was done was SNDF, which is shallow neural decision forest. So this is a model where there is no deep architecture, just the neural network part without hidden layer, followed by a decision forest layer. So here a comparison is done between this and the alternating decision forest, which is another approach which was proposed in 2013. So here we see that the shallow neural decision forest achieves better average error. I mean, this value which we see is the average error, and this is the standard deviation for 10 repetitions of the same experiment. So it's a better result than the alternating decision forest. Taking the experiments further, a deep neural decision forest architecture was designed from the Google LayNet architecture, where each softmax layer was replaced by a decision forest. Each of these forests consisted of 10 trees, each with a depth of 15. So the resulting decision forests are referred to here as DNDF0, which is closest to the raw input. The middle one is DNDF1, and the terminal layer of decision forest is referred to as DNDF2, which is this one. This network was trained on the ImageNet for 1000 epochs using mini batches of size 100 images. The results of the deep neural decision forest is also much better when compared to regular deep neural nets. So a comparison is done between deep neural forest approach and the LayNet, Google LayNet. So here the top 5 error on ImageNet for uh, deep neural decision forest is as low as 6.38%. This is the error rate, and when we compare with Google LayNet, it's much better. Here we also see that shallow decision shallow neural decision forest also performs much better than the Google Lanet, which gives us the error of 10.07, and yeah, and the other value is like 9.26, which is lower. Yeah. So um, moving on. Yeah. So this is the plot for how the top five errors change as the training goes on. So here the blue line here represents the DNDF 0, which is closest to the raw input, and this red would represent the entire network. So green and magenta represents DNDF1 and DNDF2, the other two decision forest layers. So so this plot shows how the error changes over 1000 epochs, and this is the plot for from epoch 500 to 1000. So here we see like there's a steep decrease in the error, which is obvious for many uh, for any neural network or any learning approach. We expect this to happen. The initial few epochs to have very high uh, decrease in error rate, and to stabilize or to change uh, less as the training proceeds. So yeah, so this is 500 to 1000. The change is in this way. As we can expect the blue line to have the which is for DNDF0, which is closest to the input layer. We expect this to perform worse than the DNDF2, or the other layers, which is somewhat removed from the input layer. So yeah, so the taking the mean of all the three uh, DNDFs, we get to an error of 7.84 here, like for the red line, which is for the entire network, taking the average. This is 7.84 after 1000 epochs on the validation on the validation set. Um, so this histogram shows the split of the responses of all nodes of the architecture on the ImageNet validation data. So this specific histogram is after 100 training epochs, and this shows the histogram after 500 epochs. So as training progresses, the split approaches more towards 0 or 1, so which corresponds to eliminating routing uncertainty of samples when being propagated through the trees. And in this slide, this is the final histogram after 1000 training epochs. Here we can see all three images. So this one is after 100, this is after 500, and this is after 1000 training epochs. And we can see here that the split becomes more prominent, successively more prominent in these images. So the split is most prominent in the final in this final histogram. Conclusion. So now we arrive at the conclusion section. So mm, this paper illustrates how to model and train stochastic differentiable decision trees. It's very interesting to see how decision forests can be used as classifiers for end-to-end training in convolutional neural networks. Um, this this allows us to take advantage of the representation learning enabled by CNNs, and uh, also allows us to take advantage of the uh, better classification of decision forests. So, to sum up once again, deep neural decision forests attempt to combine neural networks and random forests or decision forests. The motivation behind it is that neural networks are good at learning feature representations, and random forests is good in dealing with uh, dimensional data classification. And another advantage of this is that it is more explainable than fully connected classifiers. The results of the experiments, which were discussed in the paper, shows that it performs better than traditional CNNs. A comparison was done with Google LayNet on the ImageNet dataset, and the results were uh, better than the LayNet. The experiments with the shallow neural decision forest, which did not have hidden layers, also show some interesting results, because uh, since it performed better, uh, it it indicates that the decision forest as a as a classifier layer for neural networks can outperform traditional approaches. Um, so yeah, thank you. Here are the references and links to some papers. So this is the paper which was discussed today, and here is a link to a GitHub repository by Liang. This is an implementation of deep neural decision forest in Python. Thank you.